Some sounds appear higher or lower to our ears than others. The term we use to describe this relative characteristic is pitch. Pitch depends chiefly on the number of times each second that the air pressure fluctuation on your ear is repeated. Listen as we cause a stretched string to vibrate 440 times a second. Here now is a human voice with vocal cords vibrating at the same frequency. Now listen as we hold a piece of cardboard against a revolving gear. The gear teeth are striking the cardboard 440 times a second. Here are these same sounds again. Notice that the pitch of each sound is the same, although the sources are different. The pitch is the same because the vibrations striking your ears are repeated the same number of times per second. Now, if we double the frequency to 880 times a second, the pitch sounds higher. But the pitch of an 880 cycle tone does not sound exactly twice as high as one at 440. Of course, some persons have been conditioned by their familiarity with musical intervals, such as octaves, to think that doubling or cutting frequency in half is the same as doubling or cutting pitch in half. However, psychological tests have shown that pitch and frequency of pure tones do not have a simple one-to-one relationship. For example, many persons would judge that this tone is one-half the pitch of this tone. Although the pitch may sound one-half, the frequency is not. The frequency of the higher tone is 500. The lower tone is 200 cycles per second. Apparently, we cannot depend on our ears to determine relative frequency, nor can we use frequency numbers to designate relative pitch. The two are not linearly proportional. Science has, however, worked out a subjective pitch scale for pure tones. The commonly chosen reference frequency is 1,000 cycles per second. The tone you heard is designated to have a pitch of 1,000 subjective units, sometimes called mels, M-E-L-S. Mels from the word melody. A tone with a pitch twice as high is designated 2,000 mels. Actually, its frequency is 3,120 cycles per second. A tone which sounds to our ears 3 times as high as the reference is said to have a pitch 3 times as high, 3,000 mels. Actually, its frequency is 9,000 cycles per second. As you can see, a mel scale provides an objective means for comparing pitches of various pure tones. Although pitch depends chiefly on frequency, it also varies slightly with the loudness of a sound. Listen as we play 2 pure tones, one softly, then one loudly. Which tone has the lower pitch? Actually, both tones have the same frequency, 200 cycles per second. But the louder tone sounds a little lower pitched to most persons. In fact, experiments have shown that in general, low-frequency tones seem lower pitched when played very loudly. On the other hand, high-frequency tones seem higher pitched when played very loudly. To be sure, the difference in pitch is very slight. Nevertheless, it is discernible to some persons. Many sources of sound have certain frequencies of vibration that are determined entirely by their inherent properties, such as dimensions, the material they are made of, and shape. If set in vibration and left by itself, such a source will continue to vibrate freely and produce a tone of constant frequency which will gradually die away as the vibrating energy dissipates. For example, a tuning fork struck and left by itself, and a stretched string that is plucked. Are examples of free vibration. It's also possible to force a sound source to vibrate at frequencies not natural to it. For example, the tuning fork you just heard has a natural frequency of 433 cycles per second. We will now place an electromagnet between the prongs of the tuning fork and pass through the coils of the magnet an alternating current of some other frequency, say 428 cycles per second. That's the sound of the tuning fork vibrating at 428 cycles per second. What happens is this. The alternating current changes the magnetization of the magnetic core, which in turn alternately pulls on the prongs of the tuning fork at the same frequency as the current. So the fork, although it has a natural frequency of 433 cycles, is forced to vibrate at 428 cycles. Listen again as we switch the driving frequency on and off. You will hear the fork attempt to vibrate at its natural frequency. Then you will hear beats as the fork vibrates both at its natural frequency and the driven frequency. Then you will hear it settle down to vibrating only at the driven frequency. When we switch the current off, the fork is set free to vibrate at its natural frequency again. Now let's change the frequency of the current in the magnet gradually. First, we'll drive the fork at 420 cycles. As we increase the frequency of the current, the pitch of the tuning fork will also increase. Notice that as we near 433 cycles, the sound becomes louder. Then as we pass higher than 433, the sound becomes softer. That was an example of a phenomenon called resonance. When the forcing vibrations have the same frequency as the natural vibrations, they coincide and reinforce each other. Here's another example of resonance. We'll strike a tuning fork and hold it near another tuning fork that has the same natural frequency. Then we'll stop the first fork from vibrating. That's the sound of the second fork continuing to vibrate freely after being started in resonant vibration by the first fork.